Hello, everyone. Welcome to Foresight's Biotech and Health Extension Group, sponsored by 100+ Capital. This is the first keynote meeting of this year. We had one meeting already a month ago in which we just discussed general goals for this year. Now in this meeting, we're going to specifically focus in on the health extension industry and discuss what specific areas in the health extension industry are left underexplored, where a new project or an alliance could make significant progress. And to provide you a little bit of a context for that, this year, during the first half of the year, we shine light on a potential area for radical progress that are still left underexplored, and such as today's focus on industry. And then in the fall of this year, we will be supporting efforts for solving them via an accelerator-like structure. And we have just opened applications for this accelerator. And you can review our mentors at the bottom of our keynote program, which is accessible via the Foresight website. So I'll quickly share my screen just to give you an understanding of where to look in case you want to apply. All right, so if you go on our website, under program, so up here on Biotech and Health Extension under program, you'll be directed to the Biotech and Health Extension program. And here you'll get just a brief introduction of what this group is about. And then we had the January meeting already with goals. Today we're in the February meeting. We'll discuss industry blind spot, and we'll have a variety of different meetings in which we discuss a variety of different areas in the first half of the year. And then in the second half of the year, starting really in late August, we're going to be discussing, we're going to have a space in which different projects, so this is all of you guys who are making progress on aging, can apply to join our accelerator. What this means is that we have a variety of mentors, including Steve Horvath, Niels Rager from Apollo VC, Aubrey de Grey from Sense Research Foundation, Andrew Scott, Jim O'Neill from Sense, Reason from Repair Biotechnologies, Joe Betz-Lacroix, Tina Woods from Glider Health, Morgan Levine from Yale University, Gordon Lau from the University of Zagreb, Daniel Bocher from Harvard Wiss Institute, Joris Dillon from the Max Planck Institute for Aging, Kristen Fortney from BioAge, Felix Faber from Cambridge, Margareta Colangelo from Longevity Technology, and Peter Samek from Longevity Tech Fund. All of those will be mentoring projects, and you can apply via the application form right up here. And once you have applied, we'll be accepting you if you are not already in the group, into the group. If you are already in the group, then to take some time during the September until December in which you get mentored by the mentors. We have some financial grants available as well for your projects. And then in December, we're going to do a final report out and hopefully get you much more follow-up funding. So if that sounds like something that your health extension project could make use of, then please apply now. Applications are now open. And yeah, I'm really, really looking forward to lots of fantastic applications. I know that a few projects already were forming in the group, but yeah, we want to cast a broad net. So please don't feel constrained by the topics that we'll be discussing throughout the next months. This is definitely just a few suggestions, but you know best, I think, with your local knowledge, what kind of project is needed right now to make progress. So I really look forward to your applications, and let's turn back now to the topic of today's meeting. Today we have one of many sessions through the first half of the year in which we explore specific areas and shine light on specific areas in which perhaps a project could make significant progress still. And today we're going to be focusing on what areas specifically in the industry are underexploited for potential progress. And for that, we have Mike West, Pfleger, and Sonia Arrison here to give 3 times about 10 minutes presentations answering the questions, which are the top 1, 2, 3 areas in the industry that are significantly underexplored for progress. And then we'll discuss as a group. And to participate, it would be fantastic if you haven't done so, you want to take a look at the second document that I shared. And that is, I'm going to share it again, just for those that are late. That I think you should have that in the Zoom room now as well. So this one is the document on which we collect a few challenges. So if you want to voice your opinion there as well, then please do that on that challenge doc. It will be the basis from which we will suggest that accelerators potentially pick areas from as well. Okay, So I already added Mike's and Sonia's suggestion to that doc, but I think we should hear it from themselves. So I think Mike West, welcome to Foresight's Biotechnology and Health Extension Group, sponsored by 100 Plus Capital. It's really, really nice to have you here. Would you care to start us off, and then we'll move through Carl to Sonia?
You're muted, Mike.
Now can you hear me?
Perfect.
Sorry. Okay, so as I would propose that there's several major unmet needs that we ought to be thinking about, and several technologies that could be brought to bear on those needs. First, in regard to the unmet needs, there's a growing interest in aging research, dramatically increasing over the last few years compared to the last few decades. And a tremendous amount of that interest is focused on life extension. And arguably that's a really exciting area. And we have evidence now in numerous species that lifespan can be extended by various means, typically by metabolic interventions. I would argue, however, that focusing on life extension is not in the best service of mankind. And I'm sure immediately everyone's going to misunderstand what I'm trying to say. So let me try to clarify. I'm 100% in favor of life extension, the extension of human lifespan, and I think it's a very honorable goal. The concern I have is being part of the baby boom population, but regardless of whether you were part of that generation, the boomers represent some 76 million Americans, and they're already in old age. So, extension of lifespan is not a particularly useful modality. I would argue that the largest unmet need that we have is for treating chronic degenerative diseases associated with aging. These are accounting for nearly 80% of the over $3 trillion in healthcare expenditures in the United States. Why? I mean, obvious maybe. If you have chronic arthritis or heart failure or whatever, it's with you every day. It's a COVID-like experience that you cannot escape from. And typical current modalities, small molecule therapeutics and so on, are ineffective. They can't regrow your heart or regrow your cartilage. So what I'm saying is, economically, and for the benefit of humanity who's suffering because of aging, these degenerative diseases are by far and away the most strategic target, economically and to alleviate human suffering. Second, I would argue that the most powerful interventions in aging will actually come from technologies that could have a direct impact on chronic degenerative diseases. We call this new technology induced tissue regeneration. And just in 2 minutes I have left, I'll try to briefly summarize what I'm thinking here. Early in human development, our bodies can regenerate scarlessly. So if you're just 1 day old when you're born, for instance, and you had a heart attack, which doesn't happen, but if you did, based on all the data we have in animal models, mammalian models, and some data in humans, your heart will regenerate and heal itself scarlessly. If you're 65, for instance, and have a heart attack, you have scar tissue, permanent heart damage that could lead to death and or heart failure. The same is true throughout the body. Skin heals scarlessly earlier in development. It's part of human biology. It's not something unreachable. It's something we all once had. That biology is now within our reach to induce in an adult human using reprogramming technologies. This is sometimes called partial reprogramming, using transcription factors that can take a cell back in time, all the way back to the first stem cells of life, induced pluripotent stem cells. Similar technology can not only reverse all known markers of aging in human cells, but can induce that regenerative state. And the evidence suggests, at least in our minds, that could be for virtually all somatic cell types or all tissue types, for heart failure, for CNS regeneration. And there's a significant amount of evidence in support of this, both in the laboratory experiments being conducted over the last couple of years, but also in various animal models. Animals like the naked mole rat that we all know can live an extraordinary amount of time for a rodent is locked in this primitive state where it can regenerate. And so I would argue that a very unexplored and yet very powerful modality for intervening in aging, for lifespan, certainly, but most critically for inducing tissue regeneration in the context of chronic degenerative diseases of aging, is the most strategic target and probably eventually will become the major focus of interventive gerontology in the biotech and pharmaceutical sectors in the coming years.
All right, great. Thanks for your opening statement. If there's a clarification question, that is fair game now, but otherwise I would say we leave it for the discussion. Any clarification questions?
Not for me.
I hope so. All right, thank you, Mike. Carl, do you want to go next?
Mike, nice job. You were like under time and everything.
Okay.
So
I'll talk some more then. Didn't realize. Okay, go ahead.
If you want to, no. Okay, so let me just first of all put in a plug for AgingBiotech.info in terms of looking for what is under invested or under resourced in terms of areas. Though one of the reasons I made AgingBiotech.info grew out of my investing is I was looking at things like breakdowns of companies by hallmarks of aging or by SENS area. And that tool is partially specifically designed so that you can easily sort by area and figure out what areas don't have enough companies in them. And so, people should use that as they decide what companies to form. And, you could use that for an exercise like the sort of underexplored topic emphasis of this meeting. But I'm going to talk about something that in sort of things that are underexplored, not from a sort of a typical aging category breakdown like SENS or hallmarks. I want to talk about primarily two things, but I'll mention a third real quick at the end, that I think are underexplored due to sort of systemic reasons that this is sort of a wish list, not I have a good solution for it. So hopefully we as a community will come up with a solution. There's a lot of work on this. So the first thing is sort of better assays or ways to look under the hood inside the black boxes in biological systems. So we have biomarkers, and there's lots of, for good reason, there's lots of explosion in work on biomarkers. But most of that work right now in terms of aging biomarkers is black box whole organism biomarkers like methylome clocks, and that area is relatively well resourced and researched at the moment. Slightly more under the hood are breakdowns according to those same category breakdowns of the field, like biomarkers or clocks that are actually aligned specifically to specific hallmarks or SENS areas or other kinds of categorizations. And people are now starting to work on those. That hasn't received as much work as the sort of whole organism methylome clocks or aging clocks. But people like Morgan Levine has research going on to sort of create methylome clocks tuned to different hallmark areas. And there's other people doing work in that area. There are companies even exploring things like how do you measure senescent cell load, and that kind of thing, I think is the next level to accelerate. It's not just accelerating because you can do faster trials that read out without having to wait the lifespan of the species in question, but you can actually look at whether your mechanisms are correct. But even under the hood, one more level, we need better assays to sort of see what's going on inside. And so if you look at like engineering disciplines, right, if there's a box that does some job and it's broken, you don't generally poke at it from the edges and treat it like a black box. You unscrew the panel and look inside, and you can much more quickly figure out what's wrong or how do you make it do what you want it to do. And similarly in computer science, I'm a computer scientist by educational background, and there's a big flood into this field and interest in aging from computer scientists. And of course, most computer scientists, as they enter the field, they all chant biomarker, biomarker, biomarker. And that's because computer scientists are very used to dropping into debuggers or inserting print statements and seeing exactly what's going on in the middle. And in biological systems, that's much, much harder, but we need more of that. So we need ways to track the intermediate variables in metabolic pathways, in other biological processes, intermediates and long chains of chemical reactions that are important for aging, because the interventions need that to be able to verify that they're even working the way we think they're working, or to debug quickly if they're not. So to just take some examples, for example, Unity's failed trial for osteoarthritis in the knee, right? We don't even know the high level, did it really clear the senescent cells and then simply not have the follow-on effect, or did it fail to clear the senescent cells enough, right? Those kinds of questions need to be able to be answered faster. And that's going to require new technology and new techniques. And those advances will probably come from fields other than the aging biology longevity field specifically. And in fact, companies, to the extent to which they are created and can sort of satisfy those needs, will probably not specifically be longevity industry companies. They'll be able to serve lots of other pharmaceutical development and other biological problems and other scientific research in academic labs. So as an example company, one of the, a company that came through sort of in the San Francisco Bay Area launched, and disclaimer, I'm an investor, called Corellia Biosystems, is sort of has an assay for proteins that's sort of better than ELISA in the sense that it requires much, much less blood. By requiring much, much less blood, you can take protein samples from mice longitudinally as part of preclinical trials and actually figure out better what's actually happening in metabolic pathways than you could if you needed enough blood to kill the mouse completely. So that advance of the way that they do that has nothing to do with trying to look for reversal of aging or extension of longevity or anything like that, but more techniques along those lines that allow us to sample biological systems better to find out what's going on inside are, I think, going to accelerate all of biology, but are going to be especially important for longevity. Another example is, I don't actually know much about the stem cell history, but how long did it take the stem cell field to figure out that the stem cells were mostly dying and not, and that signaling was actually a lot of the way that their beneficial effect was felt, right? If that had happened faster, how much faster could overall progress in the field happen? So that's my first thing. It's coming, and I don't know how to incentivize. I think there are big financial gains to be had if that technology comes along faster. But right now, the backward chaining incentive signal in terms of economics is broken, in the sense that it's very hard to take those future gains, which will be diffuse across a lot of places, and cause that to create a good opportunity for a new company to come along, because they're not going to necessarily directly find a way to reap all those financial beneficial rewards. So we need some other way to jog that system. Okay, so second thing, I think we need in this field a lot more emphasis on combinations of therapies, right? So, Aubrey used to talk about robust mouse rejuvenation, but nobody's really pursuing that anymore. And we have ITP, but it's not really exploring the full cross-product space of combinations. We really need more work that combines significant therapeutics that come from different areas that address different sense damage categories or really attack different hallmarks, and start seeing how much we can crank. And it's just not feasible to do that directly in humans first. And even in terms of things like dogs, which are shorter lived, it might be too hard to do that. Maybe mice There's some reasons why mice aren't so great. Maybe there's an intermediate, I don't know, where it's like short-lived pets that are even shorter lived than dogs, like hamsters, gerbils types. I don't know. I'm not sure what the right way to jog that system loose, but we need some way to incentivize the combination things better. So those are the two that I mostly wanted to just mention. Just to throw off something, a third pet peeve of mine that I would love to see more of, but I don't know how to make it happen, is there's too much emphasis on chronic diseases of aging, which is really only start to become clinical when you're pretty old. There's quite a bit of aging that makes life worse in, after you get out of your prime of life, the sort of 20s and 30s and into the 40s, 50s, and 60s, but still before you get the clinical chronic diseases. And, I kind of think this is probably going to have to wait in line behind making progress on the diseases that are actually killing people. But it would be interesting to see some companies or some research really focused on reversing some of the things that make life worse in your 40s and 50s and, giving you back. And, maybe there's some ways to capture money from, for example, the sports field for those kinds of things, because lots of professional athletes degenerate due to aging to the point where they cannot no longer play. And I think there's probably room for companies to come along and use aging science to help therapeutically rejuvenate some of those professional athletes back to their prime competitive levels, in ways that would also dovetail with chronic diseases, but might be, fundamental in a different way. So those are my three.
Nice. Okay, three clear goals. All of them quite ambitious, I think. Sonia, would you care to share yours?
Yes. Yeah, that was a really interesting series of thoughts there, Carl. With that, I think actually things like sports medicine and the reproductive area as well, reproductive technologies, those things actually tend to drive a lot of corporate incentives. So yeah, interesting to bring it up and think about it. There's a lot of something like Fitbit, right? I mean, not that that's a longevity tech necessarily, but it helps us measure where we're going. And that was, directly aimed at people in the fitness industry. So, so I just picked sort of the top three things that I would like to see as an investor, not as a scientist, of course. I know there's a lot of scientists on the call, but the immune system, obviously COVID has hit, it's kind of slapped us in the face a little bit that we should be really looking at the immune system. I mean, I think in the past, the immune system, to the extent that industry was focused on it, was like autoimmune diseases, because there were a lot of like sort of middle-aged people getting autoimmune diseases. And why? It's like people didn't really care about the old people. Of course, old people are getting immune problems because they just get old, and that's just something that happens to everybody. But I think now with COVID, there's more people thinking about, oh, hey, the immune system has this huge function in our body, and we really need it, and it really declines with age, and that's associated with everything, right? Everything and we're all going to get it, even if we're not old. I mean, we will be old at some point. And so it's our problem. And I think that served as a bit of a wake up call. And so like, if you think about a couple of years ago when Intervene Immune got all that press, the Nature article, for regenerating the thymus and literally turning back the clock, at least epigenetically, that was pretty epic. And that, I feel like that's sort of a beginning. And so if we can have more people working on thymus regeneration, different strategies to do that, I think that would go a long way, and probably could get a great amount of funding, not only from, maybe in the corporate world, if it could get to a company stage, but at least for certain with the NIH and NIA. So I think that's one area to be looking at. I guess the second area I'm always talking about is regenerative medicine, because I feel like I'm saying this all the time. I feel like it really looks so promising. 5 to 10 years ago, new bladders were made, new windpipes were made for real human beings with their own stem cells. Like, these were not lab animals, these were real people. You saw the kid who got the bladder walk on stage at TED and talk about how his life changed from basically nothing to everything. and in terms of quality of life. And what's happened since then? I feel like the field has really stalled in the sense of new innovations not hitting the market. And I'm not quite sure why. I don't think it's a science problem. I think there's other problems. If I'm wrong, somebody please correct me. But and that goes to, I mean, one of you had mentioned, you know, growing new hearts and, you know, and things like that, you know, and maybe Mike West mentioned that. You know, maybe we don't even have to regrow the whole heart. Maybe we can just inject some factors in there and help repair the heart, maybe without so much scarring. And maybe we go along in that direction. And I do know that there's researchers working on that. But it would be nice to, you know, like what happened to Doris Taylor with making the new hearts? She was at the Texas Heart Center. I assume she's still there doing it. I haven't talked to her in a number of years, but I would like to see more of that. I think that's, I still think it's promising to repair people. And we should work on that. We should still work on the systemic stuff too, but the repair stuff just feels like it's a lot closer and maybe more low-hanging fruit than the other stuff. And then the last thing that I would mention is the brain. You know, the brain used to feel completely off limits. It was just this complex thing that we couldn't even see, let alone try to touch. We didn't understand it. You know, and so much work has been done now, you know, with the mapping of the brain, the Allen Brain Atlas, the Human Connectome Project, the Federal Brain Initiative. You know, I know there's a researcher at Stanford who I personally support philanthropically, who's growing brain organoids, literally little brains in the lab, and he's doing experiments on them, and it's really amazing. And the brain is something that is almost there, and I think we should have more people focusing on it. So I think I'll end my comments there.
Nice. Also quite the concrete laundry list. And for those who want to look them up again, at least Mike's and Sonia's points are already on the doc that I shared. And Carl's will get them afterwards.
I'll
on
have mine next week.
Perfect.
I forgot to say, you didn't mention vitamin D.
That's a different log jam. I'm working on that one separately.
Okay. Everyone take your vitamin D.
Yeah, he's still full steam working on it.
VitaminDforall.org. You can go and read about it.
Well, maybe share the link again in the chat, just that everyone's aware. But for now, I think we had Tom Khalil already with a question. And, you know, to everyone else, please collect both questions and comments in the chat. So if you have a question or you want to follow up or even object to any of the things that Sonia, Carl, or Mike has said so far, please do so in the chat, and then I'll take you on here into the discussion. Or if you want to open up your own bucket and drop something into the head that hasn't been named yet, then please do so too, and we get it on the video as well. Okay, Tom, do you want to start?
Sure. Yeah, this question was for Michael, but other people who have reactions as well, which is number one, what do you see as the most interesting work going on in this area, both in academia and industry? And number two, has anyone done a good job of articulating the open research issues? A more general point, which is, I think it's useful if we can not only say, hey, we're underinvesting in this, but to figure out whether there's some structural reason why that's the case. So a good example would be private companies will underinvest in clinical trials that involve off-patent drugs, because so that might have a really high social return to repurpose them, but the private return may be low. So trying to figure out, you know, if you think people are underinvesting in a particular area, is there some underlying structural reason why that's the case? And then we can begin to figure out what are some of the levers for addressing some of those structural barriers.
That was a question for me, correct? The most interesting academic work. So I guess that this bears on both of both categories of questions you asked. The fact that it was possible to reprogram You remember the old floppy disks? You'd put them in. Carl, you remember? You're the computer guy. You put in the old floppy disk and you hit initialize, and just it sets it back to kind of like factory specs. I guess you can still do that with your laptop, right? The fact that a cell from the body could be reprogrammed back to beginning of life was incredibly counterintuitive. When Dolly the sheep was cloned back in '98, or when it was published in '98, the scientific community rebelled, said this is a fraud, it's impossible. Of course, it was quickly shown that it actually can be done. So if the genome is like the memory on a floppy or other kind of memory device, it can be reprogrammed. And the fact that that reverses aging markers in cloning was in the year 2000. In IPS, where you use defined factors to reboot a cell back to the beginning of life, the fact that that reverses aging using all known markers filtered in at various time points, 2010, 2000, whatever. The concept of taking, so IPS reprogramming, indeed won Shinya Yamanaka Nobel Prize. So it was very quickly adopted, unlike cloning, by the scientific community as being factual. The idea of taking cells part way back in time to this regenerative state I was referring to, or induced tissue regeneration, or ITR, or partial reprogramming, everyone has their own name for it, is just about 5 years old. I mean, and then it was patent filings. Just last year, David Sinclair at Harvard got this cover article in Nature on reversing aging using this technology. So it was, just weeks or months ago. So, in terms of investment and why hasn't the industry progressed more, it's brand new. It's to the point where, there's these stages you go through where at the beginning people say it's not true, and then you adopt the truthfulness of it, so you say it's not important, and then, you go through all those stages. And this is right in the transition, I would say, from, I think the majority of aging researchers are really in the weeds on things. I think they accept, I kind of did an informal poll with some of these individuals, and there's a consensus that this technology reverses aging and probably induces this regenerative effect. There are companies forming. We've formed one called Reverse. Stanford Group has formed one called Turn, like turn back the clock, and Sinclair has started one. I think it's called Iduna. So, it's early stage.
Thank you. Carl or Sonia, do you want to chime in, or next question?
I want to push on that if no one objects. And I think, I think that partial reprogramming, if we can call it that, is really like a holy grail of sorts for aging, and that like we are not going to make meaningful impacts like the way I think most people in this room would like without being able to achieve it. However, I don't think that it's even remotely possible in situ without substantial advances in synthetic biology. This idea that you can pull cells with subsets of Yamanaka vectors in addition and push them to just the right amount is great in a dish, but if you want to do this in a living organism where you have your biodistribution curves not flat, the state of the cells are massively heterogeneous, and you need to have like really complicated control logic to get them back to the right state. And I think like if I wasn't obsessing so much on delivery at the moment, I would probably be obsessing a lot more about synthetic biology and the control logic in the body in general. But I don't hear a lot of people talking about this, and I think that it's really what's keeping something in the dish right now instead of going forward into actual therapeutic or translational work.
Well, why isn't that just a simple targeting rather than more complicated logic? Like, why can't you use, the stuff Ocean is using in terms of targeting a particular expression pattern?
Well, to be clear, Ocean's technology is involved in some of these efforts, but I think the main issue is that you have a whole bunch of different cells in a whole bunch of different states. And so I mean, think about it this way. How do you know from a purely a genetic or transcriptional activity point of view when you've reached the right spot? I mean, you look at how these things are described. If you look at paper out of Stanford guys, they're like, well, we pulsed it for a few days and we got it to the right spot. It turns out 3 days is good, 4 days is not. Like that's something you can control in a dish, but you can't do in vivo. And so I do think this idea, Carl, about of using the kind of Boolean logic approach is something we'd want to do, but it's complex, like an order of magnitude harder, because it has to work for every cell that the particle can touch. And so I've done some work on this already, trying to put things like this together. It's not an easy problem. And I think it could use some serious full-time work.
Okay, let me push back on your criticism from the other direction. To rephrase what you said, like in a Petri dish, when you've got a flat set of cells that are all the same, you can tune your partial reprogramming timing to be the optimal level. But what about a lowest common denominator, right? If you just do it, the minimal amount that sort of doesn't get you into problem anywhere for any tissue in the body, it won't be the optimal point for a lot of them, but it will still potentially reverse some degree of aging in a lot of them.
I mean, I think it's an interesting idea. My first reaction is that it's given the kind of exponential difference between biodistribution of a vector in vivo, it's going to be very difficult to do this. Let's just say we want the liver because you can hit the liver easy. The liver is going to take, orders of magnitude more of the particles in the next tissue. So you have to have a very low dose to make sure that the liver doesn't get turned into a tumor in this case. And by that point, you're not even going to be the ballpark for other stuff. And since the liver already has a lot of regenerative capability as it is, it's probably not practically the best target for that. So I think that the idea isn't irrational. I think that from a practical point of view, though, it's very difficult in a living organism.
All right, we have.
Can I comment on
Mike, go for it.
I agree with the need for assays and markers. One that we've published is a COX7A1. It's a marker of the transition called the embryonic fetal transition. It's a very effective marker in all cells except for blood cells, as far as we know. It's for every cell type in the body. So, I mean, there's others which we don't talk about. Assay development is certainly critical. I agree on the the challenges of delivery. Sinclair proposed using adeno-associated virus. We're a public company, so we don't talk about precisely what we're doing, but I think we have indicated that gene therapy approaches are first choice. And logically, what companies typically do is they target a serious life-threatening disease that is compartmentalized. So you're not doing a total body systemic treatment in the first clinical trial. And that's a typical logic, and certainly one that's not escaped our notice and our attention.
Cool. So here's an interesting, just a thought experiment. If we say built a construct that had the factors we want to express, with some restriction enzymes built in that were relatively long, and then we put homing mega endonuclease under a promoter responsive to COX7A1, can you basically cause its activation or deactivation to simply chop up your construct and have a break put on based on that pathway specifically? Does that make sense?
Yeah, well, that's an interesting thought. So, I mean,
I played with these circuits a bit, but I like them.
Yeah, I mean, I mean, so obviously we're trying to design a delivery vehicle, and then these assays would be not part of the targeting vehicle, of course, for the therapeutic suited for human use.
Well, I have a delivery vehicle for you.
That's feel free to email me, mwest@agexinc.com.
All right.
All right, we have a few more comments on that particular point from Lynne and from Jean-Hebert.
Okay, to start off with, I'd like to thank Mike, because I am 100% behind the idea that actually what makes aging really miserable is the long-term chronic conditions. And it's the non-sexy ones, it's the incontinence, it's all the undignified stuff that you don't realize until you're actually caring for some very old people. Yeah. And then you see it and think, really, I don't want that. Yeah. There's a quality of life issue, but there's a massive economic issue. So the last 5 years of life costs more than the whole of the rest of life put together in terms of healthcare costs. So there's a massive market. I mean, if you're an investor, it makes sense to invest in this. The market is vast. If you're a human being, it makes sense to invest in it because of the quality of life and the relief of suffering. So Mike, I'm completely with you on the quality of life stuff, and not lifespan extension for the sake of it, but health span extension, which will have the knock-on effect of increasing lifespan. But in terms of the reprogramming, I put a comment on the chat about the real huge difficulties with stem cells, and at the moment being in the very early stages of understanding that differentiation pathway and going treading that incredibly fine line between hyperproliferation and hypoproliferation and cancer. And I love the comment that when we can cure cancer, actually, we're not going to be bothered about that. But unfortunately, at the moment, I don't think we're quite there. But there's one way of doing it for certain cells, tissues, and organs, where you can get the best of both worlds, where you do the ex vivo programming in dishes, and then you put the engineered tissue back in. So there's some work at in the UK, Imperial College are doing Band-Aid for the heart, essentially. So they're growing stem cells, they're putting them in patches. You can actually have minor surgery, put over the infarct, repopulate. And that's one way of exploiting the regenerative properties without having the cancer risks. But that's not going to work systemically. I don't really know what is. I've put in the chat also a link to Oxstem, which is a company that's been out from the university. I'm not involved in it, so I'm not selling it from a personal point of view. But they're looking at small molecule reprogramming specific to individual cell types to try and tweak regeneration in vivo. Mm-hmm. So and then we have had the field. The whole waters have been muddied by certain people claiming things that turn out not to be right. So again, I put in the chat about the issue with regenerative medicine and the claims that you could regrow a trachea on a scaffold and implant it. And the surgeon was so well looked at that nobody dared question the fact that actually more patients died than lived. And the scandal finally broke. And I think we have to be incredibly careful about the speed at which things move, so that you don't let some stellar people get their own way and then create something that's going to destroy the field, put it back 10 years like genetic engineering did when there were the studies where people got cancer from some of the genetic engineering stuff. So we have to move at a rate that's appropriate to the science and not push it too fast. But I think the science is getting there. And I love this idea of the ex vivo reprogramming and then being able to patch up certain tissues. So I think that sort of covered some of the stuff I put in the chat. Thanks, Alison.
Thank you. And if anyone of you wants to react, Carl, Mike, or Sonia, otherwise we'll have.
Can I make one comment on that? Yeah, I thought that'd be brought up earlier. This idea of reversing aging using reprogramming technologies is, I want to make 2 points. One, yeah, to me, the challenge and the issue that we're going to be facing is the concern about cancer. 100% sure of that. So because what isn't yet completely known publicly is these same pathways are being used heavily by cancer cells. So cancer cells are sort of regeneration out of control. And a lot of that data will be, made clear in coming months in the scientific literature. Now, but it'd be guilt by association if we therefore said that that's a big problem. And in fact, many of these animals that have this profound regenerative potential have almost no cancer. And where the science is at right now, we actually think we know why that works. And so it addresses some of these issues of cell senescence. If a tissue can regenerate, then and if the cells are senescent or have serious DNA damage, what we do is we keep them around, and it causes us all these aging problems. That's the whole logic of senolysis. You know, how do we get rid of these zombie cells? But if you're in this regenerative state, they just explode. They're apoptosed away. And so that reduces the risk of cancer. So number one, the big thing that the scientific community, and it's where I agree, that we focused on is, can we safely reprogram and reverse aging using this technology without increasing the risk of cancer? And that's what FDA, I'm sure, is going to be their number one concern and the big burden.
Mike, in regenerative reptiles that apoptose the senescent cells so much better and avoid cancer, is that immune system modulated or something else?
Yeah, there's some speculation that it is, but I don't think so. I think it's just a form of apoptosis. The the P53 pathway, for those of you that are into all this nuance, that can induce senescence instead will induce apoptosis if you're in that regenerative state. A second point, which also was brought up, is the nonsense factor. We've never had the gerontology community, the medical research community as a whole, now with a journal called, Nature Aging, serious science talking about age reversal. And we're now entering that era. We really think this is real science. If there was a lot of nonsense about stem cells in regenerative medicine, and believe me, there was massive misinformation about, I won't point fingers, but a lot of misinformation out there. Can you imagine what it's going to be when, the snake oil salesmen start hearing about age reversal? So we really do need platforms like this and others to communicate where the real science is and where the schlock science is in the coming years.
Thank you.
Can I ask has there ever been a good model of sort of like self-regulation in terms of a group of, because you can also imagine a group of scientists just getting together and going, oh, they look like they're going to beat me. They're snake oil, and try, so how do you, but Mike, that is it's such a good suggestion, because it is a big danger. How do we, and maybe this is a topic for another time, but how do we set this up so that we can help that?
I don't like these, they're these industry groups. And again, I'm not pointing fingers, but I mean, people love to form these industry groups, the Regenerative Medicine Industry Organization, some such thing. You can imagine, and they'll set standards. Early on in the stem cell field, we had the International Society for Stem Cell Research, right? And they would put an impromptu on, whatever they thought was real science or what wasn't, although they didn't really go after the nonsense all that much. I don't know the answer. Sonia, why don't
Have you ever looked at the aviation incident reporting system? It's an extremely successful system for anonymous reporting of anomalies in a cockpit where there's no questions asked, and it is almost singularly responsible for the fact that commercial aviation is the safest form of travel when measured per mile or per seat.
Right, so maybe it's done on the consumer end. Something bad happens and something's reported. Is that what you're saying? Yeah.
Yeah. It's almost like you whistleblow on yourself, but get away with it because it's anonymous, because the institution recognizes it's better to let them get away with it once than for it to remain a systemic problem in the system.
Can I also raise
Aviation
some
incident reporting system.
I was going to say that
Anyway,
we ought to
sorry for
actually allow
interrupting.
people to publish negative results.
What was that?
We ought to allow people to publish negative results rather than always saying that every Cell and Nature paper has to be the most interesting, novel thing ever. If people hide their data, we don't have this anonymous reporting of things that go wrong because you can't get it out there in the scientific literature. So I absolutely agree with you, David. I think that we're not safe because we don't report the negative stuff. because there isn't a vehicle for reporting the negative stuff. So I love what you're saying about the aviation industry. Sorry to have interrupted you.
Can I add something?
Yeah. Yes.
Briefly?
Yeah. Go for it. And then wait, Keith also wanted to chime in on this one, and then we're going to continue with the questions.
No. It's just because it has to do with reprogramming, and we're on that topic now. So I'm a huge fan of reprogramming. It can have a lot of applications, but I think it will fail in terms of reversing aging in an organism. I mean, Matthew pointed out some of the reasons why implementation would be very difficult. And if even think of how you might do that in the brain, which is even harder to access, and we might consider that to be an important organ. It becomes very difficult to imagine how it might be implemented. But beyond that, I think one of the main reasons it'll fail is because it doesn't address a large fraction of the damage that accumulates with age, which is extracellular, which doesn't get turned over. So you can change gene expression all you want, and it won't reverse much of the damage that occurs outside of cells. So, I think it could have some benefits for sure, as Mike has pointed out. But in terms of reversing aging or even, significantly slowing, a lot of the damage that occurs to our proteins and carbohydrates that exist outside of cells and that don't get turned over much in life and that contribute to the frailty of aging, I think, that's we have to admit the limitations of the approach, I think.
When you lob a leg off from my axolotl, Mexican salamander, you could have this tattered and frayed appendage. And what happens is a family of cell adhesion molecules are pulled together and the tissue is remodeled as a blastema. And the whole blasted leg regrows with all of its complexities, all of its articulations and tendons and muscles and everything else. To say that this will not work in a context of turning over matrix, extracellular matrix, I think it's too early. I would argue it's too early to say. We have reasons to believe that the early embryonic state
But Mike, in the example of the axolotl, it's all new cells. You're talking about existing cells, which is completely different.
No, I didn't.
Cells in tissue. Now you're talking about replacement, which will absolutely work. You're right. So if you can replace organs by regrowing them, that will work.
I didn't mean to imply that it was a remodeling of existing tissue in the axolotl, but my point is if you think about the complexities of what the tissue is doing to recognize the damage, and then, like I said, it's not a clean break necessarily. It can be tattered and frayed, and these cells can recognize the trauma and reorganize matrix and other things to reorganize and generate a nearly completely normal limb. I think we ought to be slow to be quick to assume that it can't remodel ECM. In the early embryonic stages of development is when a lot of the elastogenesis is occurring, for instance. There's all these fibrillins and elastin-associated proteins that are laying down in the elastic matrix, for instance. And some of the preliminary data suggests that ITR, partial reprogramming, can reinduce an elastogenic state, for instance.
I mean, we can go on discussing this offline. I'd love to do that, but all these examples are very different than the adult, unless you're talking about injuring and removing tissue and having it regenerate, which is, I'm all for that.
I guess my point is
that will reverse aging, but
very good question, and the jury's out, and we'll see.
Yeah.
Well, maybe, John, I bet you can address that when you have your focus talk in a few weeks from now. Yeah? Does that sound good?
And Mike, I hope you're there.
Great. Okay, lovely. So next up, we had Keith with a quick comment on this, and then we had Robert Simon with a general question moving on. Great.
Yeah, it was actually on the previous topic about the snake oil stuff, so I'll be brief. But I just wanted to point out that there are existing models we can follow just in the normal world. For example, clear codes of journalistic ethics. I've been noticing that there's a lot of sort of emerging news sites happening in our field that really aren't following proper journalistic ethics. Diligencing the stories before they're just sort of recommunicating it out, or not properly disclosing conflicts of interest, right? So one of the things that we're starting to push out soon is basically writing up a tailored version of journalistic ethics for our field specifically, with some additional things that should be met. So I think that will help to at least have a litmus test to be like, does this story hit that or not, to help sort of tamp down on irresponsibly shared information. It's not the whole puzzle, but it's a piece.
Great. Well, maybe you can share that with us, and we can add and discuss. Thank you. Robert, you had another question.
Yeah, thanks for inviting me to stay here. So I'm just wondering if there's any interest here in like technology platform or drug delivery platform development. So there's a lot of discussion here about what can be done with existing tools and approaches, but as Laura Denning, for example, often points out, maybe improving the tools is really what's needed to advance the state of the art in biology. And just a comment there. So the Paul G. Allen Frontiers group, I think I sent out something out to the mailing list. They have a $10 million ideation challenge exactly along these lines. So I'm just curious if there's any interest and if this would fit the accelerator goals.
Yeah, well, we kind of had suggested a few potential focus areas of interest. So instead, like in addition to the more general meetings that we have, where we kind of survey a specific section, such as industry now, then research next, we also do specific focus topics. So one of them is specifically on biomarkers, one is on biomarker standardization, and one is on platforms and tools. And so there we have in total, I think 6 folks, all Foresight Fellows, who will be discussing their current data and AI research in health extension. And from that, we hope to extract a few more enabling technologies. But if anyone has more suggestions from that, then please point them to the keynote. Yes, Mike, you have a few more.
Well, like I'm not quite your time. I apologize if I am. Maybe my hoarseness is my body trying to tell me to shut up. I really feel a really valuable tool could be accomplished. It just needs money. And it would be a tool that would be used for millennia, absolutely foundational. And that would be, let's just call it age map. It would be to, on a single, this is all, doable technology today. It would be to map every RNA transcript, which is the messages of life, right? Every mRNA by RNA sequencing, and the chromatin structure of on a single cell level of resolution. So, like a high meg, picture on a single cell resolution of aging tissues in the human body. It would be then could be plugged into AI and be used by researchers, and would be an absolutely incredibly invaluable way to study aging, because you could then query it for, as we were talking about extracellular matrix or anything else, you could quickly look at, is the type 2 pneumocyte in the lung doing what during aging and when during aging? If we had that map, and it's simply a matter of money, you could plug it into all these companies that do next generation sequencing and so on. You could generate this massive database, and that'd be the type of thing, if the Paul Allen Foundation or others would fund, would be used by medical researchers all over the world for millennia to come.
And that's kind of like the Zuckerberg Human Cell Atlas project has sort of started doing, right? Just needs more money to make it more complete.
Yeah, we started a thing called LifeMap, which was LifeMap Discovery in particular, which was mapping the cells, and simply ran out of money. Yeah.
More broadly, Robert, I think that the Allen ideation challenge on tools is very much in the same spirit of what I talked about first, about but I was talking about a specific subcategory of tools, namely ones that are sensing based, not just arbitrary tools. And, you know, Paul Allen has a lot of money, and it's great that he's going to put up 10 million in funds. But, you know, I think the broader problem with incentivizing tool development is that it's not commercially a great invest, you know, it's not a very lucrative way. So there's not enough commercial development incentive economically to.
What about Illumina sequencers? I mean, I agree.
You know, Illumina is a great success story, obviously, and you know, it would be interesting to see a business case study of them, right? Like, is that, you know, is it really a standout? Like, is it the 1 in a million company that it was so successful? Or is it successful because it happened to hit a Moore's law kind of thing right at the right time, and it benefited from that? But how many Illuminas do we not know about because they died, and only the successful do we know about? I don't know, but lots of these other tool breakthroughs are kind of come opportunistically when the science and the technology make them available, but there's not as much funding driving toward them, I don't think.
Yeah, so that's another question. I mean, how do the electron microscope manufacturers and cryo-EM and all that kind of stuff, extremely expensive pieces of equipment for now, right? And they're still being sold and they're still being manufactured. So is there a distortion in the types of investments that are made from venture sources because of the need for strong profit, or not? It's just another point that I thought I would bring up.
Google Earth.
One second, Mike. Before you jump in, I just want to say it's now 1 minute past the hour. So in case anyone has to drop off, and with that I mean also Carl, Mike, and Sonia, I want to give you an easy out. I just want to not miss to thank you very, very, very much. I know that all of you have very, very full schedules, especially right now. So thank you very much for making it today. You're welcome to stay on. I'll still be here for a little while. Apart from that, we have our next meeting again in a month from now, and I'll be following up with videos. But please feel free to stay on. I just wanted to give you an easy way out and not miss to say thanks.
I'm going to say goodbye. Thank you very much.
All right, thank you. Well, bye-bye, Sonia. All right, so for those, let's see, who want to stay on, I would love to know a little bit in more detail what kinds of platforms or tools you were thinking about. Like Robert, what kind of platform were you envisioning? Because I think it's easy to say enabling technology, but like, is there a specific one, for example, like the one that Mike discussed, that you think would really, really help specifically in the health extension field? Because we talk about enabling technologies and and those kinds of platforms all the time, even in the molecular machines group. But is there a particular area, especially right now in biotech and health extension, that's interesting?
Well, here's an idea. This is all, this sounds like an ideation discussion anyway, but here's an idea that I hadn't heard elsewhere. I'm just putting out there, it's obviously, these are technically very challenging things to do. So, one of the reasons why there might be less interest in pursuing them is that they're just very hard problems. It's harder to develop a new instrumentation or technology than it is to pursue some kind of like conventional therapeutic development, probably, even though the therapeutic development is incredibly complicated as it is, right? It's so risky. But here's an idea that may help certainly in case of aging, biology, longevity therapeutics. What about creating an artificial model, something like an organoid system? Of course, this is probably still the future, but one which ages faster than normal. In other words, so that you can test all of the interventions on something, you can compress what would normally be an 80-year lifetime of aging into like 8 months or something like that, right? And then it has like the correct correspondence. That would be very useful, right? And I haven't seen any discussion of it.
Seems like it would be really valuable to make an organoid model with knock-in progeroid genes. That'd be one way of doing it.
It's too bad that Mike, it looks like, left the call right before you said that. So, I mean, part of his work, they're talking about manipulating the epigenetics, not only to move it in the youthful direction, but to move it in the faster aging direction as well. And, you know, that's not so much, there are other benefits of that besides, as, you know, faster test cases to test anti-aging. You know, it's potentially a cancer therapy, for example. So if you can make the cancer cells age faster, then that might help kill them.
I mean, we have that. It's called a mouse, but it's not, obviously it's not human DNA. So we're wondering, is it really aging? But, you know, then you could take something like, you could take stem cells from a Hutchinson-Gilford progeria patient and grow them in culture, and that has some sort of accelerated aging. But then you're still asking, well, yeah, but is that really aging? And so I think in order to get something that is doing accelerated aging, you have to tell it to do something different from a normal cell, which means you have to think you know exactly what aging is by like making that thing happen. And then if you're using it as a model to try to reverse the aging, you're basically trying to undo this thing that you already know the answer to.
I agree with Joe there. I think that we could put in a progeroid gene and cause something to age faster. And then if we took out that progeroid gene, we'd say we'd cured aging, but no, we just returned it to normal.
I mean, if I can just present a thought experiment here.
Yeah.
This is science fiction, right? But if you could create a virtual human, right, that you can run in a simulation, then you can definitely run it faster than real time in the simulation and still have correspondence to what's going on. Of course, this is science fiction, right? This is far away, but like there are people working on this. I think the compbiomed.eu is very far advanced in this area, and there's a virtual rat, there's the open worm, but maybe there's some kind of hybrid approach that uses organoids or some physical model that can then be simulated out. And if you can get the simulation to correspond to the properties of the physical system, then you can certainly run the simulation faster, and it will.
I want to do.
Right, I thought.
Yeah, so I think it would be easier to combat aging than to devise a model of aging. Certainly 3D organoids are better than cells in culture because you have those, but there's still a long cry from the mixture of you know, post-mitotic cells, really matured extracellular matrix, and cells, some of which are still proliferating. So organoids are usually cells that are growing, and so they're very different. So that wouldn't necessarily work, but the bigger problem is you know, biochemists have looked at the complexity of aging like decades ago, right? And the different types of damage like is incredible. Just to proteins, for example, there's dozens of different cross-links or covalent modifications that occur to proteins. Never mind DNA, fats, carbohydrates, and probably we only know a fraction of them. So I think modeling that is going to be exceedingly difficult. Maybe, like you say, science fiction in the future.
Well, does Gail Pagano?
I think we will have to make more progress on aging before we make sufficient progress on that for it to be really useful.
Gail, any comments, or Cosmo?
Yeah, the lab I did my PhD in was working on protein modifications in skeletal muscle in diabetic and aging people. And I concur with the notion that simulating that is a total mess. I don't think that would necessarily be workable. Then again, putting together a resource of a fairly sizable aging cohort of people and getting that kind of proteomic data would be very valuable, I think.
What's the kind of tool that you'd like to see, Cosmo?
I'm always gung ho on multi-imaging. That's my current technological obsession. So my goal is to create effectively a core facility where tissue sections or sections of organoid tissue can be multi-imaged, which would give you a pixel-wise determination of the full mass spectrum. So you could effectively quantitate metabolites in tissue at every single location in a tissue, and then compare that to age. I think that's very similar to what like Recursion Pharmaceuticals is doing, but they're doing it with optical microscopy with maybe 4 color channels at a time. But if you could do that with mass spectrometry and get thousands of metabolites at a time, that would be hugely powerful as a resource.
Any comments to that?
Well, the question is, how do we incentivize? You know, if we had that, it would have so many applications and it could capture so much, you know, if it were priced at a fair market value to recoup a reasonable profit margin relative to the value it brings, it could make a huge amount of money. But it's hard to, you know, how do we actually bridge that gap to, because the huge amount of money would come from a wide variety of different places.
How about we bridge the gap by helping Cosmo form a company and fund it?
Well, I'm talking more about the helping Cosmo form a company part is the easy step. I'm talking about how do we get the, you know, the future potential income of such a thing to actually make the investment attractive enough. I think there's a problem there capturing all those future gains in tool companies like this.
I gave up on the business side a long time ago. I'm not a business.
Can I ask whether we need to know what we're looking for before we build a platform to look for it?
I'm definitely a fan of going fishing, so I tend to take the opposite approach.
Yeah, I think your point when you're doing science, it's good to have a model, you know, biological understanding and have a hypothesis and stuff like that. But then when you're actually doing the work, you want to have the broadest tools possible so you can get the serendipity moments and things like that. That's where the breadth is good.
No, I'm just wondering, are we looking at things that hang around for microseconds? Are we thinking of things that hang around for years? Are we looking at proteins? Are we looking at short-lived metabolites? What would your platform be able to assess?
And can
I love the idea of it.
Can it look at live tissues, or are the tissues dead when they get taken apart by this apparatus?
Are these questions being directed at me regarding multi-imaging?
Yes, you are being quizzed. You're now.
Okay, so a typical industry application for multi-imaging, and that's, you know, full disclosure, I'm at Vera Biotechnology now. That's where I landed. I haven't made any public announcements of that because complicated reasons, but a typical industry use for something like multi-imaging is to take a section of, say, a rat brain that's been treated with some drug, and then image that brain and see what parts of the brain that drug actually penetrated into. So pharmacologically, it's a really useful procedure for determining drug penetrance and absorption in different endpoint organs. But for something like aging biomarkers, I think it would be a really useful application for determining whether or not certain metabolites pool up in aging organisms, whether or not there's effectively like a metabolic backlog for some mitochondrial metabolites, for example. Or in the case of protein accumulation, you could use it to assess whether or not certain proteins are accumulating in certain organs, like the brain, which, as we know, is a hotspot for protein accumulation in aging humans.
Can I just add a comment to the point that I think it was Lynne made? So this whole discussion around hallmarks of aging, following these the papers in 2013, 2014. I'm not an expert, but on those specific papers, but if I'm not mistaken, there was no real discussion of the quantitative levels of change, only the approximate rough, like, qualitative change in each. And I was doing some literature review around like telomere measurement, for example. And apparently, according to at least some of the telomere researchers I found, this is still an open problem in the telomere research space, how to measure telomeres and harmonize the measurements. So another basic thing that might be useful to the field would be just a standard set of measurements for each of the hallmarks. And then are the hallmarks actually totally comprehensive, or are they just a convenient mental box of the various things that are going on? Just a thought.
I know I hogged the conversation, Alison. Can I come back on that one? I completely agree with you. We lack quantification in anything. But the problem is everything depends on your cell type, your organism, the inducer of the aging process. So not just chronological age, but the biological age from the tissue you took it from. So what are you actually measuring when you're saying, we measure a hallmark of senescence? Yes, we can measure how much reactive oxygen species there are in a mitochondrion at a particular point in time. And we can say that that comes from a senescent cell. But is that reflective of a senescent cell in you versus me versus my tissue culture dishes? I don't know. So we can quantify for the condition that we have, but we can't quantify and make it a universal. So I don't know if that answers your question at all, but the quantification is so dependent on what you're looking at that I could give you a number of quantities for, I've done quantitative proteomics on senescence, so I could tell you for a particular skin fibroblast grown in a dish for a particular condition, how many of a certain type of protein molecules there are. But I don't know if that tells us anything about the aging process or what happens in a real complex system. So Rob, how would you do it? What are you actually specifically asking for?
I don't know the answers. I'm simply pointing out that it's a little funny that at this day and age, something like telomeres, 30, 40 years of research, and there's still no standard approach amongst the researchers in the field themselves that they can agree upon. I saw a paper in 2016 where it was clearly stated there's no standard agreed upon method of quantitation. So it just seems like one of the necessary and immediate steps to make progress in the field. Just start with this basic stuff. It's not easy to do or I mean, it's tedious and it's annoying maybe, but and it doesn't necessarily lead to exciting headlines, but it's just an obvious step to do. So like the Hallmarks 2013 paper, I'm quite sure there was no quantitative description of the changes there. So maybe there's an update that I'm not aware of. And I'm not an instrumentation expert. I'm very interested in that area and thinking of trying to study it a little bit in the years ahead, but I just feel like it's very important. So all this stuff about measurement, instrumentation, quantitation, and to your point about how it depends what you're looking at, well, that just says that it's very complex. So measure as much as you can until you can properly identify what it is that you're measuring. Then you also have the measurement problem, right? Like,
yeah, there's finite resources, and part of the problem is that nobody, there's not enough money, especially money from government or wherever, just for this basic research to sort of take a systematic view and try to say, we're going to develop good quantification of every hallmark. That would be a huge process. So instead, people in the field run around to what they think is important. There's not been a lot of fixing, coming up with the final answer for telomeres, because for lots of people think telomeres aren't that important, right? And until, and part of that's because the easier thing to measure was the average telomere length. And then as people figured out that it's actually the critically short telomeres that matter, well, now so more people are actually thinking, okay, now maybe telomeres are worth looking at, but it's only when you count the short ones, which is harder to do. But so in the meantime, people were running around to the other hot areas. And so, senescent cells are obviously have gotten a lot of attention. So there is more work now trying to quantify those, but it's not easy necessarily to quantify those in different tissues. But that's, but clearly because of the obvious prominence and importance of senescent cells in recent years, there's actually a lot more work in that area. So I think you kind of get the profile of the quantification work gets more and more improved in whichever areas seem most promising.
What are other areas apart from telomeres? If you could say, okay,
all the hallmarks. All the hallmarks. What are, I'm not an expert in this, so I'm just saying, like, what are the best available current methods for quantifying them? This is not mentioned in the hallmarks paper.
Same for
well, that's a nice one for the accelerator. Yeah.
you know, quantifying is much harder than just identifying, right? So it will follow, but it takes a while. And, you know, the SENS areas, to the extent to which they're different, slightly different from the hallmarks, have the same problem. So, you know, it's not easy to measure what is your total glucosapine, AGE cross-link burden in tissue. But, you know, those things will come. Well, maybe they won't. You know, some people will say that fixing it is actually easier than quantifying it.
Joe Betts, you're still on the call, aren't you? If I recall correctly, 2 years ago, you were leading an effort to put together a standardized database of these various assays for these various hallmarks.
Yeah, well, it turns out to be a very hallmark by hallmark thing. You know, like each one of these hallmarks is a whole area of biology unto itself. So it's not something that you can just kind of do by saying, okay, we're going to quantify these. It's like, oh, you have to become a specialist in cell-to-cell communication. They're also very vague. They're like giant categories. So you can't just like quantify intracellular communication, and then have a single scalar variable that tells you like how good it is or not. You know, there's like a million different protein variants circulating in a mammal that are going back and forth between cells, and that's, you know, then there's interactions between them. So now you have a billion, and so, you know, like if you're working on some very specific part of the biology of intracellular communication, like specifically how, you know, some, you know, muscle satellite cell is talking to some nearby progenitor cell or something, and a specific part of their communication between them, that's the area you're focused on. And great, you could probably find the particular signal that they're passing back and forth. And that's the thing you could measure for that particular thing. But in a way, it's kind of an ill-formed spec to say, let's just quantify all these.
On that subject, is there any sort of like, you know, reliable level of correlation for, say, you know, age linking, right? You know, is it the same? Is it fair to say that the progression in skin is the same for internal organs? Then could you use skin measurements, you know, wrinkles and such, as a proxy for an overall measure, or is it, there's no guarantee that it maps uniformly in any way?
Well, I hate to be boring here, but it's like, what are you trying to measure? Are you trying to guess someone's chronological age? Are you trying to figure out how long it is before they're going to die if nothing is done?
The question there specifically was, is there a way to put a number on how progressed age linking is? So I'm just speaking.
Oh, age linking. I see. Got it. Yeah.
I mean, you know, Keith, as an example here, you know, you can look at skin aging on different parts of the body and, you know, look at the huge difference in aging of the skin of the parts that are exposed to the sun all day, like in the face, versus in the parts that aren't. And there's a pretty big difference. So
aren't there particular systems, at least for many people, that tend to, how can I say this, age more quickly? And what I mean by that is they cause trouble, like the vascular endothelium. You know, this is the thing which gets AGEs piled up on it and loses its flexibility and eventually gets all inflamed, and then you know you have a heart attack. I mean, can't we just look into particular tissues which are, you know, the kind of weak points of most people's bodies?
Who's the right person to ask for this kind of topic? Like, is there someone in this network that is working specifically on this kind of instrumentation stuff, or?
I think most people narrow it down to something that's measurable, like Steve Horvath. I mean, you get the methylation clock, and you've got tissue-specific methylation clocks, and you've got global methylation clocks, and you've got Grim age. So he's the most quantitative person there is, but he's not going by the hallmarks. He's just going by, does this tell you how long you're going to live for? Or
right. So Morgan Levine is working on some methylome clocks that are going to be tuned to the different hallmarks. But you know, in order to train that, she has to have assays that evaluate the hallmarks to begin with. So, but in general, the instrumentation problem is going to come from people outside this community, right? The people who are die hard working on aging first and foremost are, you know, are plugging at the individual things that need to be, you know, that will make progress. And, you know, the trick is, how do we look around at the things, the wider world, and figure out which new or almost ready advances in instrumentation can be pulled in and used right away.
Yeah,
Well,
right.
I could go around in our other groups, because even, you know, as I mentioned, in the molecular machines group, we often have similar types of requests. And then, you know, I could see whether we can crowdsource it from the community. Like, I think, because oftentimes when we do technical competitions, many folks that are working on instrumentation, they don't really know what's needed. So there seems to be a real communication gap between those that are needing the tools, but they don't really know who are making them. And then those who are making them, but they don't necessarily really know who exactly would like to use them. So if there was a concrete shopping list, I could try to look around and see if there's someone either already working on it or at least interested in working on it. And one more thing, we have Steve Horwath joining our group on June 22nd, in case you have a specific question in that area for him.
One way to measure or look at age cross-linking in the cardiovascular system is rather simple, and that is to take the blood pressure, the systolic minus the diastolic. That pulse pressure difference gives a good idea of the stiffness of the large arteries. And you can also do some imaging of the heart to see if the left ventricle is thickening, indicating more resistance from the peripheral blood circulatory system.
And you can also do that thing with looking at like the sound wave or the echoes from the heartbeat bouncing off the arteries. I'm not getting it exactly right, but there's a new test, relatively new, that just uses like a standard cuff, but has a higher frequency capture, and it actually sees the vibration or stiffness of the arteries. Kind of a generalization of what you said about systolic over diastolic, or minus diastolic.
Yeah. On this,
and also, you could look at the Horvath age, and you're not going to see whether or not the extracellular matrix is cross-linked. That's sort of separate from Horvath aging.
Glycan age, doesn't that get it all? Or is that antibodies?
I'm not sure.
Yeah, on the spirit of this, I think an important tactic that's kind of emerging from this conversation is, and I'm noticing traction in certain large private companies here, the more that we can correlate some internal measure, like if you can get that same measure, you know, either it's imaging your heart, or if there is some more easily collectible physiological telltale of it, something in your voice, something in your eyes, etc. The more that we can set up correlations between those things, the more I think we can, you know, use those proxies to leverage like massive data collection initiatives that would do something useful. And that's personally where I'm finding real buy-in on massive private companies. So I think there should be some intellectual power to making these correlations where we can, to link some sort of external measure to some sort of internal measure as best as we can. And I think that will open the floodgates to traction here.
Is was it that MIT group you mentioned doing the audio-based diagnostic, or the other examples?
That's the one clear example. I can't get into specifics, but I could say that things have gone well there, and something massive is underway with upgrades of that. So.
Okay, any other questions or comments? I would say that if not, I'm going to open up the gather room, which is, you know, usually what we did after the normal meeting, we always moved into breakout rooms. Now we have the gather space by which you can just sit at tables, talk to each other in a much more decentralized way. So I think, you know, it could be a fun one to try.
Thank you, Allison. I have to sign off. Thank you for.
Thanks, Carl, for joining. I know that you're very, very busy. I really appreciate that you took the time. And I'll see all of you again for the next proper meeting soon. I'll be following up with bits, but those who are interested, I'll meet you in the gather room to sit at tables and chat. All right, well, it was really, really, really good to see all of you. And I'm hoping that you'll apply to the accelerator or share it with other projects. It's a little bit of a different type of accelerator in the sense that yeah, they come with no strings attached, so we're not taking any shares right up front or anything. It's really just trying to see whether those people that are already on these calls could actually help projects along in a more systematic way, rather than what we're doing on the calls. So take advantage of that if you want to. And yeah, I see many of you in the other room. Bye bye.